Machine learning, ML, is a powerful subset of artificial intelligence, AI, that enables computers to learn from data and improve their performance over time without being explicitly programmed. At its core, ML focuses on developing algorithms that can identify patterns, make predictions, and adapt based on experience. It is commonly categorized into three main types: supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, models are trained on labeled datasets, where both the input and the desired output are known. This approach is widely used in classification tasks like spam detection and image recognition, as well as regression problems such as predicting stock prices or real estate values. Unsupervised learning, on the other hand, deals with unlabeled data, allowing models to uncover hidden structures or patterns without prior knowledge of the outcomes. Common techniques include clustering, which groups similar data points for applications like customer segmentation or fraud detection, and dimensionality reduction, which simplifies large datasets while retaining meaningful information. Examples include principal component analysis, PCA, and TSNE for data visualization and preprocessing. Finally, reinforcement learning, RL, represents a unique paradigm where an agent learns to make decisions by interacting with an environment, receiving rewards or penalties based on its actions. The learning process involves key elements like states, actions, rewards, and the ongoing balance between exploration, trying new actions, and exploitation, maximizing known rewards. When combined with deep neural networks, RL evolves into deep reinforcement learning, enabling agents to tackle highly complex dynamic environments such as robotics control, autonomous driving, and advanced game playing, famously demonstrated by systems like DeepMind's AlphaGo. Together, these branches of ML form the foundation for many of the intelligent systems that are shaping modern technology.
Deep learning is a fascinating subset of machine learning that leverages neural networks with multiple layers to sift through vast amounts of data. Imagine these networks as intricate systems designed to automatically uncover patterns and relationships, making them incredibly powerful for complex tasks like image recognition and natural language understanding. Take feed-forward neural networks, for instance. They're the simplest type, where data flows in one direction from input to output, ideal for classification but not great with sequential data. Then we have convolutional neural networks, or CNNs, which shine in image processing by detecting spatial patterns like edges and textures. They're the backbone of applications like facial recognition and medical image analysis. For sequential data, recurrent neural networks, or RNNs, come into play. They remember previous inputs, making them perfect for tasks like speech recognition. However, they can struggle with long-range dependencies, which is where LSTM networks and GRUs step in to save the day. Finally, we have transformers, a game-changer in natural language processing. They use self-attention to weigh the importance of words, allowing for efficient training and handling of complex sentences. This architecture powers models like BERT and GPT, transforming how we approach tasks like machine translation and conversational AI. Deep learning is truly reshaping the future of technology across various fields. Natural language processing, NLP, enables AI systems to comprehend, interpret, and generate human language in a way that is both meaningful and contextually aware. This ability powers a wide range of applications, from chatbots to complex analytical systems. Key models that have shaped the development of AI language understanding include GPT, BERT, and newer models such as T5, PaLM, and Llama. GPT, Generative Pre-trained Transformer, is an advanced language model designed for text generation and reasoning. Based on the transformer architecture, GPT excels at generating coherent and contextually relevant text based on a given prompt. It is widely used in conversational AI applications, such as virtual assistants, chatbots, and content creation, and is versatile enough to handle tasks like translation, summarization, and text-based games. Its ability to generate human-like responses makes it a foundational model for many AI-driven platforms. BERT, bidirectional encoder representations from transformers, revolutionized NLP by introducing a bidirectional approach to text processing. Unlike traditional models that process text in a single direction, BERT understands the context of a word from both the left and right sides, improving its comprehension of nuanced meanings. This depth of understanding makes BERT highly effective for tasks such as question answering, sentiment analysis, and improving search engines. It has significantly enhanced the performance of conversational AI and recommendation systems by making them more context-aware. Newer models such as T5, Text-to-Text Transfer Transformer, PaLM, Pathways Language Model, and Llama, Large Language Model Meta AI, represent the cutting edge of NLP research. These models are designed to handle a wide range of tasks, including machine translation, summarization, and advanced dialogue systems. T5 treats all NLP tasks as a text-to-text problem, allowing it to perform tasks like summarization, translation, and question answering in a unified framework. PaLM, developed by Google, is a large-scale language model capable of performing complex reasoning and generation tasks, pushing the boundaries of language understanding. Meanwhile, Llama, developed by Meta, focuses on building smaller, more efficient models that retain competitive performance, making them ideal for both research and industrial applications. AI has made incredible progress in analyzing and interpreting visual data. At the heart of this revolution are convolutional neural networks, or CNNs, which mimic how our brains process images. They excel at recognizing patterns and features, making them essential for tasks like facial recognition and medical image analysis. Then we have object detection models like YOLO and faster RCNN, which not only classify images, but also pinpoint the exact location of objects. This capability is crucial for applications in autonomous vehicles and security systems. On another front, generative adversarial networks, or GANs, are transforming how we create images and videos. By pitting two neural networks against each other, GANs generate synthetic data that can be indistinguishable from reality, paving the way for deep fakes and innovative art. Finally, vision transformers are taking things a step further by analyzing images as sequences, allowing for a more nuanced understanding of visual data. Together, these advancements are reshaping the landscape of AI, pushing the limits of what machines can see and comprehend. Reinforcement learning, RL, is a machine learning paradigm where an agent interacts with an environment to learn optimal behaviors by maximizing cumulative rewards. This process is typically modeled using Markov decision processes, MDPs, which provide a mathematical framework for decision-making, consisting of states, actions, transition probabilities, and rewards. One of the foundational approaches in RL is Q-learning, a value-based method where an agent learns the expected rewards of actions in given states. However, traditional Q-learning struggles with high-dimensional state spaces, which led to the development of deep Q networks, DQN. DQN combines deep learning with Q-learning by using neural networks to approximate Q values, enabling agents to handle complex environments such as video games. Beyond value-based methods, policy gradient algorithms focus on optimizing policies directly rather than estimating value functions. Notable policy gradient methods include proximal policy optimization, PPO, which balances exploration and exploitation efficiently, asynchronous advantage actor critic, A3C, which trains multiple agents in parallel to improve learning stability, and soft actor critic SAC, which incorporates entropy regularization to encourage exploration. These advancements have significantly improved RL efficiency, making it applicable in fields like robotics, finance, and autonomous systems.